Okay, we're gonna look at some more examples. Here, we're gonna see that there might be a number in front of the radical. If there is, we're gonna multiply it with the number that we take out of the radical. So in this example, this 6 is just hanging out in front here. So it's really 6 times radical 24. We don't need this dot here to show multiplication when the number is next to the radical symbol. It's just implied that these are being multiplied. So the 6 is just going to hang out in front. We're going to simplify the 24. 24 is not a perfect square, but there is a perfect square factor inside of 24. So I could do the factor tree, but me personally, I can see what the perfect square factor is of 24. I know that 4 is a factor of 24 and 4 is a perfect square. So I'm going to go ahead and split up this 24 to make it 4 times 6. So I'm going to put the 4 in its own radical and then the 6 in its own radical. Remember that this is the product property of square roots. Okay, so now we're going to multiply the 6 times, we're going to take the square root of 4, which is 2, and then this 6 is just going to stay underneath the radical because it's not a perfect square. Finally, let's multiply these numbers in the front. 6 times 2 is 12, and then radical 6. And that's our answer for this one. Let's take a look at number 8. Number 8, we have 9 times radical 32. So again, I could just look at the factors of 32 and try to find the perfect square factor. But we have to be careful that we're not just finding any perfect square factor, it must be the biggest perfect square factor. So if we're looking for the biggest perfect square factor inside of 32, it's not 4. There is a bigger perfect square inside of 32. So I can see that 16 is the biggest perfect square inside of 32. I'm going to break up this 32 to be 16 times 2. The 9 is just going to stay out in front here for now. So now it's 9 times the square root of 16 times the square root of 2. We're going to take the square root of 16 because it's a perfect square. We're going to get 9 times 4, and the square root of 2 stays the same. Finally, we'll multiply these numbers out in front. 9 times 4 is 36. Square root of 2 becomes our answer. So I just want to show you what would have happened if we had not picked 16 as the biggest perfect square. So I'm going to put the example over here, 9 square root of 32. Imagine that we saw 4 as the perfect square. And if I break up this 32 into 4 times 8. But now look inside of 8. Do you see that inside of 8 there is another perfect square of 4? That means that I can break down the 8 even more. So then this 4 would be here. Let's break up the 8 to be 4 times 2. Now, if I put these two 4s together, that creates 16, and 16 was the biggest perfect square factor. So it is important to find the biggest perfect square, not just any perfect square, because in order for it to be simplified, all of the perfect square factors have to be out of the radical. If we had left 8 underneath the radical, there would still be a perfect square factor inside of there. Okay, we're going to look at some examples now with variables. Remember, variables are perfect squares when they have even exponents. So when we have any variable, we're looking to find the biggest even exponent that is a factor. Let's look at an example. Our first example that we're going to do is the square root of 6x to the third. So if I wanted to, I could try to do a factor tree with this. Well, 6 is not a perfect square, and there are no perfect square factors inside of 6. It's only 2 and 3. So 6 cannot be simplified. Nothing is going to happen with the 6. It's going to stay underneath the square root. But let's do a factor tree with x to the third. I know that x to the third is really x times x squared. And then I can break up this x squared even more to be x times x. Remember, when we do a factor tree, we're looking for pairs of numbers, or in this case, variables. So I see that I have a pair of x's. So when I go to split up this radical, I'm going to put the pairs of numbers in their own radical and multiply it by the things that did not have a pair. The 6 up here did not have a pair, and the x did not have a pair. They're going to go in the second radical. When I multiply the pair back together, I see that I get x squared, which means that x squared is the biggest perfect square factor of x to the third. Really, it's just one less than this exponent here, because the biggest even exponent inside of an odd exponent is just one less than that odd number. Any odd number minus 1 is an even number. So now x squared is a perfect square. Let's take the square root of it. I get x, and then the square root of 6x stays here like this. Let's look at another example with variables. We're going to do 3 times 40x squared. So we're going to split up the 40 because I know that there is a perfect square factor inside of 40. So if I split up the 40, I know the biggest perfect square factor in here is 4. 4 times 10 is 40, and then x squared is also already all perfect square because it has an even exponent. So now the perfect square factors, I'm going to put them together in their own radical. So the 4 and the x squared, they go together. And then the 10 is not a perfect square, it's going to go in its own radical. I can take the square root of each of these. I'm going to even put them in their own radical. 4 can get its own, x squared can get its own, and 10 can get its own. Again, this is the product property of square roots. Let's take the square root of the perfect squares. The 3 is just still hanging out in front. It's going to get multiplied with what we take the square root of. The square root of 4 is 2, times the square root of x squared is x, and then the square root of 10 is just going to stay underneath the radical. Finally, let's multiply all these numbers in the front together. 3 times 2 is 6, times x is 6x, and then radical 10 stays the same. Let's look at some more examples with variables. We're going to do the square root of 9x to the 7th y. Okay, so I'm looking at all of the parts of this radical. 9, the number 9 itself is already a perfect square. I don't need to break up 9 because 9 is the biggest perfect square factor of 9. X to the 7th is not a perfect square, but inside of x to the 7th, there is a perfect square. Just one less than x to the 7th is x to the 6th. Since x to the 6th is an even exponent, that is a perfect square. So let's break this up. So we're going to make this 9 times x to the 6th times x, and then the y is just going to stay the same. The y is really to the first power, which is odd, and I can't really do 1 less than it because 1 is the smallest exponent that it can be. So now let's split up the perfect squares so that they are in their own radical. 9 is a perfect square, x to the 6th is a perfect square, x and y are not. They're going to go in their own radical. Now we can take the square root of both of the perfect squares. Square root of 9 is 3. The square root of x to the 6th is x to the 3rd. Remember, you just divide the exponent by 2 when you take the square root. And then the square root of xy stays the same. And that would be our answer, 3x cubed, square root of xy. Let's look at one more example. Let's do 10 times the square root of 200 x to the 5th, y to the 2nd. All right, I'm going to look underneath this radical here. 200 is not a perfect square, but there is a perfect square factor inside of 200. It's 100. That's the biggest perfect square that goes into 200. X to the 5th is not a perfect square, but there is a perfect square factor, just one less than it. X to the 4th would be an even exponent, which is a perfect square. Y squared is already a perfect square because it has an even exponent. Let's start breaking up the first two that are not perfect squares. The 10 is going to stay the same. The square root of 200, I'm going to make this 100 times 2. Let's break up x to the 5th. We're going to make that x to the 4th, so just take one exponent away to make it even, and then times x. Finally, we have our y squared, which is going to stay the same because it already is a perfect square. I'm going to reorganize this and put all of my perfect squares together. 100 is a perfect square. That's going to go in this first radical. X to the 4th, that's a perfect square. And y squared, that's a perfect square. In a separate radical, let's put the numbers that are not perfect squares. This 2 is not a perfect square, and this x is not a perfect square. Finally, we're going to take the square root of all of these perfect squares, and remember, we're multiplying it by the 10 in the front. So this 10 stays here, times the square root of 100 is 10, times the square root of x to the 4th is x squared. Remember, you divide the exponent by 2. Times the square root of y squared is y. And then we're going to keep this radical 2x because they're not perfect squares. Finally, let's multiply all these numbers in front together. 10 times 10 is 100. X squared y, square root of 2x. And that would be our answer to this question.